Okay, lecture 14. This is the second part of the least squares estimate. Least squares estimate is such a useful tool that us engineers use that so often. Like, can you see the dots here? The data looks like this one here. But sometimes models may not be linear. But if the models are linear in parameters, then we can use the same linear regression model. Like this one here. Here, we have used the model AX plus B. And here, obviously, we have used a quadratic form, right? And this one matches the distribution of the parameter better than the other one, naturally. So what can we do? How can we come up with this one? Okay, so that and this. And as I said, this one is linear in the parameter, but this one is also linear in the parameter. X squared is computed, but the parameters were A, B, and C. So I'm going to repeat this one again and again. Linear in parameters. That is a catch. So we do the same thing. J is defined to be the summation of y minus this one here computed by x. So what we do is set the delta partial derivatives with respect to a, b, not only a, b, but c as well, and setting those to be 0, and from that we get pretty much similar type of equation. And if I put everything together into the vector matrix form, this is what we got. As you can see, there is a structure within the matrix, coefficient matrix, and also this one here. And a column and a row are added. If you look at the rest, this is pretty much what we had and that. But because we had one more term, so we added one more column and one more row here. And how we generalize is obvious here, right? 1 xn xn squared, xn xn squared, xn cubed. The other way around is also true. So therefore, that is going to be xn to the fourth power. And here, y, xy, so therefore x squared times y. Okay. So from this one here, probably you can tell what is going to happen when we have a fourth order equation, right? Polynomial as well. Anyway, this is the same form, so that the unique solution exists if determinant A is not equal to 0 as usual. And, well, I can say is actually the determinant is not equal to 0 in practical situation because there always is error. And x is something you can choose to distribute. Okay, so a unique solution exists. All right. The second one, linear in the parameters. So the last example was a quadratic form. So we had constant x squared term. But you can have any function for those, right? So how about this one here? Y is given by this particular equation here, where phi1, phi2, and phi(n), all of those are functions of x. But the point is a1, a2, blah, 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 an. So this entire equation is linear in terms of parameters. So that's the interesting part. Okay, so J is defined to be this one here. Once again, nothing new here. So normal equation is going to be from this one here. Remember that we had x squared, x plus 1, and then we had this. And okay, let me go back to that equation one more time. Yeah, this one here. So this is 1 was the coefficient of C, xn was the coefficient of B, xn squared was the coefficient of A. So that's what we had here, right? And if you look at this here, this y xn cubed, that is going to be the product between the coefficient of B and A. So in that respect, this is the product of C coefficient itself. So therefore, and this is what we got. Next one. Normal equation here. This is it. So this was A n. Phi n was the coefficient of A n. That's squared. And this entire thing, phi n is multiplied. And this here, phi 1 is multiplied. Phi 2 is multiplied. And over here, phi 1, phi 2, phi 3, and phi n. Voila. And here, phi n is multiplied, blah, 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 phi 2, phi 1. From here to there. So, from the other example, you can pretty much identify that this is going to be the equation you will get. And this is a normal equation which you can solve. Again, in the form of this. All right. So, the catch was, third time I'm saying this, linear in the parameter. Linear in parameters. Not the linearity of the model. The phi 1, phi 2, those functions could be nonlinear function of x squared or exponential x or whatever. So let's take a look at some of those functions as examples. Here, y is fx, which is exponential ax plus b, which is not linear. Not linear in x, nor not linear in the parameters. How about this one here? Y is equal to a times x to the b's power. It's not linear in terms of the parameters. And how about this one here? Haha! You have exponential of a times e to the bx. Exponential. This function is called a double exponential function. So what can we do? Well, if the model equation is linear in terms of parameters, then we can apply the same thing. So the technique or word what we use here is linearization. Linearize. We linearize it by taking the logarithm of both sides. So this equation and that equation, those two equations are equivalent, right? Y is equal to exponential x plus b, therefore log y is x plus b, which is linear in A and B. How about this one here? Well, we can do pretty much the same thing. Linearized model is ln y is equal to ln a. This is a product, so it becomes an addition. And x to the b's power logarithm, so b comes out. So if I call ln a to be a and b to be b, rename the parameters, then this is the linear equation in the parameter. Okay, the last one. Okay, linearized model is this one here. You take a logarithm of exponent to get rid of this exponential, first exponential, but you still have exponential here. As I said, this is a double exponential function. So therefore, you take a logarithm twice. Then what you got is this one here, ln a plus bx is the same thing as this one here. So you're going to come up with a plus bx. Again, linear in the parameter. So what we can do is we can apply the same technique to come up with the model parameters. Here's a catch though. We will minimize linearized error. Okay? Because we have to linearize the model equation in order for us to be able to use the same technique. So therefore, the error we are minimizing is the linearized EMS error, which is of course not the same as the original error. Okay, so for example, this one here, y is equal to axb, linearized model is this one here. So therefore, the linearized error j hat is going to be summation of ln y minus this thing here, x squared. Okay? So that's the error you are minimizing. But in the original equation here, the error should be yn minus a xn to the bth power, right? Squared. So that's totally different from that one. So my suggestion is that we use this error, linearized error, to find the model parameters a and b, but check the original error as well. Plug in your model parameters into this one here and compute this difference and original error. All right, let's do that with a solid example here. Find the model equation here, this one here. So the first thing you will do is to plot those points and see how it goes. It looks like exponential, right? It is always, the y value is always positive and goes to 0, close to 0 as x decreases, and as x increases, it increases very rapidly. So probably observations yk is greater than 0, and you write down those observations, and then using those monotone increasing. It's not oscillating. So a candidate model would be this one, the exponential x plus b. Okay, you can use other models as well, of course, but from those, probably a reasonable choice for the model is this one here. All right. So let's use this linearized model to come up with A's and B's. Okay, so what do? We expand this table to include those parameters, not parameters, but the values, data, which are used in the normal equation. So from x and y, original one, I have log of y, because that's the one we need, and x times log y, and x squared. So compute all of those, and then summation, sum them up to come up with all of those. So using those values, you come up with this is equal to that. So, and this inverse times that is going to be that. Okay? Easy. Once you know what to do, it's easy. Okay? So now, let's use those parameter values to compute the original error. Well, for the comparison, let's compute linearized error as well as the original error. Model is this one here. Okay. All right. So I have augmented my table with some other ones. This is a model. This is error. This is error squared in model yk, etc., etc. And you compute those. And this one is supposed to be very small. Okay, if you remember, this one can go up and down. So squared, this is RMS. This can be used for the RMS error in the linearized model. The same thing here, this could be used for the original error. Okay, using this one here, linearized RMS error, LMS, least mean squared error, root mean square. So this is R. I guess root mean squared error is this. This one divided by 5, square root is 0.255. And the original one here, using this one here, 0.23. This is error. Okay. So this is the plot of the function in the original data field. And this one here is linearized data and linearized model. Both of them looks very good, right? So that's what we got. All right. So that's pretty much is the end of my lecture of fundamental mathematics for robotics. This set of lectures will give you pretty much the idea what kind of mathematics will be used in your robotics study. When you build your robot and do experiments on it, and you do know how to do the data processing and kind of things as well. All right? And I hope you have a good time with your own robot. So I'll give you final lecture after this one.